So our first example is the bin packing problem. Given n items of different sizes, such that to simplify the problem, we assume that each size is no more than 1. It's a positive size and is no more than 1. We're supposed to pack these items in the fewest number of bins, each of which has unit capacity. Unit capacity means the maximum capacity of each bin is just 1. So it's guaranteed that each bin is large enough to hold at least 1 item. Okay. For example, say we have 7 items and these are their sizes, and they can be packed in this way, right? And this is an optimal packing. We need exactly 3 bins to pack them. Looks like a very simple problem, right? As a matter of fact, it is NP hard. By the way, the decision version is that given k bins and n sizes, can we pack all the n items? And this one is NP complete. The simplest approximation algorithm is the next fit. Next fit is to check for each item coming in if we can pack it with the previous item. If yes, we just pack it there, or else we open a new bin for this one. So this is the pseudocode. We start from the first item and then pack it in a new bin for sure, and then read the next one. If the next one can be packed in the same bin as the first one, we place them together in the same bin. Otherwise, we create a new bin for item 2, and then update item 1 to be item 2, and we are ready to read the next one. And the complexity is clearly linear, right? For we only have one simple while loop. And about the approximation ratio, we have this theorem. Say, let capital M be the optimal number of bins required to pack a list I of items. So M is the optimal solution. The next fit algorithm never uses more than 2m minus 1 bins. And more, there exist sequences such that next fit uses exactly 2m minus 1 bins. So this is a quite tight upper bound. So what is the approximation ratio? 2, right? So next fit is a 2 approximation. And since the proof is not complicated, let's have a look. Again, we prove by contradiction. And the theorem claims that next fit never uses more than 2m minus 1 bins, right? So let's assume that it is not true. So what if next fit generates 2m or even 2m plus 1 bins? Then we're going to prove that the optimal solution must generate at least m plus 1 bins, which means m cannot be the optimal solution. Now let's see how to prove it. We let S of b sub I be the size of the ith bin, the total size of the items packed in the ith bin, and then we must have the following inequalities. We say that the size of the first bin plus the size of the second bin must be strictly greater than 1, right? Because if it is smaller than or equal to 1, then certainly we can pack them together into the same bin, right? If the items are packed into different bins, means the total size of these 2 bins must be strictly greater than 1. And this kind of inequality is actually true for every pair of neighboring bins, right? From the first one to the last one, if we assume that it generates 2m bins, right? Now let's sum them up. What do we get? We get that the total sum of all the sizes, well, how many inequalities do we have here? Exactly m inequalities, right? When we sum up both sides, we get that the total sum of all the sizes is strictly greater than m. And here comes the contradiction. Why? We say the optimal solution needs at least that many bins. What does it mean? When we sum up all the items and divide it by the capacity of each bin, right? That gives the number of bins we need. So the optimal solution must be no less than this number, right? So we have that the optimal solution must be greater than or equal to this number. And what is this number? This number is the total size, right? We have just proved that this one is strictly greater than m, which is at least m plus 1, right? And that proves that the optimal solution m must be greater than or equal to m plus 1, and that is the contradiction. So next fit is simple and fast, alright, but in the worst case, the number of bins are almost doubled. That doesn't look nice. So people have tried to make some improvements. So here we have the first fit algorithm. Instead of simply checking the current bin, first fit would scan for the first bin that is large enough for this new item. If we can find this bin, we just place the item in that bin. Otherwise, we have to create a new bin for this item. Still quite simple, right? But it'll take some extra time to scan the bins, right? If we simply do a linear scan, the complexity would be what? N squared, right? And if we can carefully implement it, we can get it done in n log n time. So it's more expensive than the next fit. But is the result getting better? Here we have the theorem. And let m be the optimal solution. So the first fit never uses more than that number of bins. So it's about 1.7 m. And there exist sequences such that first fit uses exactly 1.7 m minus some number, that many bins. So what's the ratio? The ratio is 1.7, right? A little bit better than 2. And there's yet another method called the best fit. That is to place a new item in the tightest spot among all bins. Tightest means after packing the new item in, the remaining available space is the smallest. And it has been shown that it's about the same as the first fit. Still 1.7 with n log n time. Now let's get back to the previous example. So here we have studied next fit, first fit, and best fit. And your discussion question is, please take a minute to draw the results obtained by these 3 different methods. Alright? Okay, have you done it right? Everything is quite straightforward, right? Well, the difference between first fit and best fit is the position for point 3, right? For the first fit, when point 3 comes in, we just scan from left to right and find the first bin that is large enough to hold point 3. So point 3 will be here. But for the best fit, we're supposed to look at the position so that after we pack point 3 here, there's no more space left in this bin. So this is the tightest fit position for point 3. So what is the optimal solution? Do you still remember? 3, right? We should be able to pack them in 3 bins only. So next fit is the worst. The first fit and the best fit are about the same. Another example to give you some feelings about the bad cases. Look at these sizes where epsilon is sufficiently small. So what is the optimal solution? When we sum them up, when we add these 3 numbers up, it's going to be less than 1, right? So we can pack every 3 of them in 1 bin, and we only need 6 bins. However, if we pack those items according to the given order, one by one, what do we get? All the 3 online algorithms require 10 bins. Well, all the 3 algorithms we have seen are the online algorithms. Do you still remember what online means? We process the input data one by one, and at any time point, if we stop the input right there, the online algorithm will give us the correct answer for the input we have processed, right? And that's what online means. With respect to this bin packing problem, online means to place an item before processing the next one. So we process them one by one and cannot change decision. So for example, suppose that the first item we get is 0.4. So obviously we have no other choice. We have to create a new bin for 0.4, right? And next, another 0.4. So we check this bin and see that there's enough space for 0.4. So let's put it here. Next, oops, another 0.6. There's not enough space left, therefore we have to create a new bin for 0.6. So far it's okay, but next, what if there comes in another 0.6? In this case, since we cannot change our decision, we would have to create a new bin for this 0.6, right? If we know that there's going to be another 0.6, we should have created a new bin for this 0.4 instead of packing it into the first bin, right? But at this point, we cannot undo anything and therefore obtain the wrong answer. Well, the problem of online algorithm is that you never know when the input might end. So there's no online algorithm that can always give an optimal solution. And there's a theorem saying that there are inputs that force any online bin packing algorithm to use at least 5/3 the optimal number of bins. Notice here, in our textbook, this number is 4/3, and it's been updated to 5/3 by a professor in our department, Professor Zhang Guochuan, who is doing research in this area. So what is 5/3? That's 1.6666, right? Approximately 1.7. So you can see that 1.7 is a pretty much tight upper bound for the ratio. And there are actually more online algorithms, like the worst fit instead of the best fit. And that is to pack in the bin that has the largest remaining space instead of smallest remaining space. And also others like almost worst fit or any fit. And their ratios are all about 1.7. So what else can we do to obtain a better result? Well, if we can get more information, hopefully we can do a better job, right? So if before we pack anything, we can get a list of all the items, will it be better? So there we go, the offline algorithms. That is to view the entire item list before producing an answer. So what can we do about this list? Just think about the previous example when we applied the online algorithm. What are the troublemakers? What kind of item that force us to make the wrong decisions? The small ones or the large ones? The large items, right? If the small items keep coming and we have already packed them into one bin and then there comes the large ones, we would probably regret about what we have done, right? So can you see the solution now? Let's pack the large items first. So here's the solution. We just sort the items into non-increasing sequence of sizes. So the large items comes in first, right? Then apply either the first fit or the best fit. They're about the same to solve it. So it's called either first or best fit decreasing algorithm. So let's again check the previous example. Say we have 7 items like this. Step 1, just sort them in decreasing order. Okay, so 0.8 first. Now let's apply, say, first fit to pack them. Step 1, we ought to create a new bin to pack 0.8. The next one is 0.7. It needs another bin. The next one, 0.5, another bin. All right, now 0.4 can be packed into the third bin, right? So here comes in 0.4. How about 0.3? Here. And 0.2 here. And finally 0.1. Everything is perfect. We just obtained the optimal solution. Is it going to be always like this? Here we have the theorem. If you let M be the optimal solution, then first fit decreasing never uses more than that many bins. Again, this number has been updated. In our textbook, this is an integer 4. And that part, say, there exist sequences such that first fit decreasing uses that many bins. And in our textbook, this is 0. Now we have an even tighter bond. 6/9, which is 2/3, is about 0.7, right? It is a constant that is smaller than 1. So what about the ratio of approximation? About 1.2, right? Much better than that 1.7 for the online algorithms. So the point of this example is to show you that simple greedy heuristics can give quite good results, even though this problem is NP hard.